Think about it for a second. Almost all of our modern software runs on an invisible and honestly somewhat fragile engine. When we write code today, we're relying on compilers to take our human-readable instructions and translate them into the raw machine code that our hardware actually runs. But, compilers do so much more than just translate. They heavily optimize. They rewrite your loops, they reorder your variables, they strip out inefficiencies. But what if I told you the mathematical foundation guaranteeing this entire process works flawlessly? Well, it might not be as solid as we all thought. It's kind of terrifying when you really stop and think about it. How does a compiler actually know its optimizations won't silently break your code? For decades, the answer has basically been rooted in highly informal math. Conceptually, early compilers just treated code as a simple first-order imperative programming language, where memory was just this big, flat array of bytes. Whether a code rewrite was sound or not was usually just considered obvious, without anyone requiring a really complex correctness argument. But as we're going to see, that informal foundation is cracking under the sheer weight of modern hardware.
So in this explainer, we're going to solve this mystery by walking through 5 logical steps. First, the compiler's hidden engine. Second, the multi-core memory crisis. Third, rethinking static assignment. Fourth, establishing a new mathematical contract. And finally, mechanizing the proof.
Let's dive into step 1, the compiler's hidden engine, taking a look under the hood. To really understand the fix here, we have to look at how heavy-duty compilers like GCC, Clang, and MLIR are actually processing our code. Let's rewind to the 1980s. Computer scientists back then realized they could optimize way better by taking our human-friendly imperative code, the stuff with structured loops and nested math, and breaking it all down into what's called 3-address code. This basically converts nicely structured control flow into unstructured jumps between basic blocks, and it replaces all those complex sub-expressions with incredibly simple atomic steps. But even this normalized format had a pretty major flaw. A single variable could be updated multiple times throughout a program's execution, which made it practically impossible for the compiler to reason algebraically about the data flow. And that problem led to the brilliant standard we still use today, static single assignment, or SSA. SSA actually borrows a core idea from functional programming to ensure that every single variable gets exactly one permanent definition. By numbering each definition of a variable, like imagine turning variable x into x0, x1, and x2, substitution suddenly becomes unconditionally valid. You completely bypass the need for complex data flow analysis just to figure out what value a variable holds at any given time. This was a massive innovation that made optimizations so much easier to execute, and it's been the dominant compiler intermediate representation for decades now. But what worked perfectly in the 1980s is seriously becoming a liability today. That brings us to step 2, the multi-core memory crisis and where this informal math starts breaking. Because we are definitely not using the simple machines of the late 80s anymore, right? Today, we are dealing with the modern weak memory problem. With multi-core processors and incredibly complex caching layers, memory is just no longer a simple sequence of bytes. And because the traditional semantics of SSA have been handled so informally for so long, applying those informal optimizations to modern weak memory systems can lead to absolutely disastrous, unpredictable results. Right now, it's actually an open question which equation should hold true for an SSA program, and it's equally unclear which equations modern weak memory models should even satisfy. So, how in the world do we fix a broken foundation without just throwing away decades of compiler infrastructure? That brings us to step 3, rethinking static assignment to fix that foundation. The authors of this breakthrough paper mapped out a really elegant translation pipeline. Traditional SSA uses these clunky things called Q nodes to express loops, and they honestly lack clear operational semantics. So the authors just stripped them out entirely. They recast them as basic blocks with arguments, or BBA. By treating each basic block like a functional tail recursive function and inserting brackets, they sort of magically convert standard dominant space scoping into pure lexical scoping. This is exactly the kind of rigorous structure you'd find in theoretical computer science. And once we have our code in this pure, lexically scoped form, we can actually visualize the math behind it. Imagine a program fragment, let's call it P, interacting with a structured loop. This type-theoretic framework enables a really powerful property called dinaturality. I know, that sounds a bit intimidating, but it is effectively just a set of congruences and rewriting rules. It allows us to rigorously justify extremely complex multi-block code optimizations by breaking them down into simple, fully verified algebraic steps. By formalizing these equations, we can literally mathematically prove the equivalences between two completely different control flow graphs.
The underlying rules dictate exactly when it is safe to commute pure expressions over infinite loop iterations. So instead of a compiler just guessing if an optimization might accidentally break a loop, it can use these visual control flow graph equivalences to safely and mathematically justify complex code rewrites.
Which leads us perfectly into step 4, a new mathematical contract for compilers and hardware. By formalizing this equational theory, the authors have done something truly monumental here. They haven't just proposed some new syntax, they have essentially drafted a highly rigorous treaty for the entire tech world. The real beauty of this new contract is that it ends a very dangerous guessing game. Historically, compiler writers and hardware designers have been playing exactly that, but now they don't need to know each other's jobs perfectly. Compiler writers can safely optimize code relying solely upon the equational theory of SSA, without needing to know all the messy, intricate details of the hardware's memory model. And on the flip side, hardware designers can validate their new weak memory models simply by seeing if they satisfy these mathematical equations, without having to study every possible compiler optimization pass. But listen, this isn't just abstract academic theory floating around on some whiteboard. Let's look at step 5, mechanizing the proof, making it mathematically verified. This is where the paper truly shines. The correctness and completeness of this entire syntactic metatheory have been ironclad proven. The researchers substantially mechanized their proofs using the Lean 4 proof assistant. They literally verified the substitution properties for their type theory and proved that their set of syntactic equations is entirely sound with respect to the categorical structure. In short, an actual computer has mathematically verified that this logic holds together perfectly. No more it's obvious guesswork. Furthermore, they didn't just stop at pure theory. They built a concrete model proving that this framework handles realistic TSO, or total store ordering, weak memory systems. This proves that it is absolutely possible to give realistic weak memory models, which do not disturb the fundamental underlying structure of SSA. We can finally have our aggressive compiler optimizations and our modern multicore hardware playing nicely together under the exact same set of mathematical rules. So this leaves us with a pretty provocative thought to wrap up on. As our hardware grows increasingly chaotic, multi-layered, and complex, shouldn't our software's foundation be mathematically certain? Thanks to this explainer, we see that we finally have the tools to move away from the informal guesswork of the 1980s. Always keep questioning the foundations of the tools you use every single day.